something strange has happened at the edge of our solar system. A signal that Voyager 2 was never supposed to send suddenly changed. For decades, Voyager 2 has been drifting in silence, far beyond the reach of the sun, sending back faint whispers from interstellar space. But recently, engineers noticed something in its transmission pattern that didn't match any known fault, glitch, or space weather event. The signal wasn't weaker, it wasn't broken, it was different. Tonight, I'm going to show you what changed in Voyager 2's data, why scientists at NASA's Jet Propulsion Laboratory took this anomaly seriously, and how one tiny shift in a deep space signal raised questions no one expected to ask. By the end of this, you'll see why some researchers quietly said, this shouldn't be happening. Voyager 2 is more than a spacecraft. It's a time capsule launched in 1977, built with parts older than most of us watching right now. It has crossed the heliopause, the invisible boundary where the sun's influence fades and interstellar space begins. Out there, it flies through a sea of charged particles, cosmic radiation, and magnetic fields that no human-made object had ever touched before. So when its radio tone shifted in a way engineers couldn't immediately explain, alarms didn't go off. Something worse happened. The room went quiet. Because in deep space, silence usually means death. And patterns usually mean intent. What Voyager 2 just sent back forced teams at NASA JPL, working with data from the Deep Space Network and comparisons to Voyager 1 telemetry records, to double-check everything they thought they knew about how machines behave beyond the edge of our solar system. The change was subtle, but it was real. And once they saw it, they couldn't unsee it. This isn't a story about aliens landing tomorrow. This is a story about how a 8-year-old spacecraft drifting in the dark reminded us how little we actually understand about the space between the stars. And once you see what the signal did next, you'll understand why some scientists said this moment felt wrong. When engineers at NASA's Jet Propulsion Laboratory first noticed the change in Voyager 2's signal, their first reaction wasn't fear, it was disbelief. Spacecraft don't just change how they talk to us, not without a reason. Every tone Voyager sends is tied to a specific system on board. Power levels, temperature sensors, plasma readings, antenna alignment. For nearly half a century, those patterns have been boringly predictable. This time, the pattern shifted in timing, not strength. The signal arrived on schedule, but the spacing between pulses drifted slightly, not enough for a casual observer to notice. Enough that Deep Space Network receivers in California and Madrid flagged it as unusual. When the team compared it with Voyager 1's telemetry data, recorded by the same network and analyzed using the same software, the difference stood out even more. At first, they blamed cosmic noise. Out there, beyond the heliopause, Voyager 2 moves through interstellar plasma. Charged particles slam into its instruments, and cosmic rays can flip bits in memory. Scientists at NASA JPL deal with this kind of thing all the time, but this wasn't random noise. Random noise is messy. This pattern was smooth, consistent. It repeated. To be safe, engineers ran the data through old fault models written decades ago, some of them created by people who have long since retired. Nothing matched. They checked antenna pointing angles, temperature drift, and power decay from the radioisotope generator that's been slowly losing strength since 1977. None of it explained the timing change. So they looped in outside eyes. Researchers at the Harvard Smithsonian Center for Astrophysics reviewed the signal behavior. Teams familiar with Arecibo legacy data patterns compared it to known space interference signatures. Nothing lined up. Even scientists who had worked with the Hubble spectrograph on faint signal extraction said the pattern looked intentional, not broken. Then came the uncomfortable part. The change in timing began right after Voyager 2 crossed into a region of space with a different magnetic field structure, mapped earlier by Voyager 1 and confirmed by plasma wave data. In simple terms, the environment around the spacecraft changed. And right after that, the signal changed too. This raised a question no one wanted to say out loud at first. What if the environment wasn't just interfering with the signal? What if the environment was shaping it? Out beyond the heliopause, space is not empty. The European Southern Observatory and Keck Observatory in Hawaii have spent decades studying how interstellar clouds behave, how magnetic fields twist and fold, how charged particles form invisible currents. Voyager 2 is flying through that sea right now, carrying metal, wiring, and antennas that were never designed to operate in that kind of environment for this long. Picture throwing an old radio into the ocean and being surprised when it starts sounding different. Except this ocean is made of radiation, plasma, and magnetic waves stretching for light years. Still, one detail kept bothering the engineers. If this was just interference, the changes should have been chaotic. But the pattern held. Voyager 2's power is fading. Its systems are being shut down one by one. The spacecraft is dying, slowly. And yet, this signal change didn't look like decay. It looked like a response. This is where the problem really began. When the Deep Space Network ran longer captures of Voyager 2's transmission, the pattern didn't drift randomly over hours or days. It adjusted in steps. Small, consistent shifts, like something nudging a metronome out of sync on purpose. Engineers at NASA's Jet Propulsion Laboratory hate that kind of pattern because machines fail in ugly ways. They don't fail politely. To rule out Earth-based causes, they compared signals picked up in California, Spain, and Australia. 3 different antennas, 3 different pieces of ground hardware, same strange timing shift. That killed the idea that a local glitch was messing with the data. Whatever was happening, it was happening to Voyager 2 itself, not to our receivers. Then they pulled old records. Telemetry from years earlier, back when Voyager 2 first crossed the termination shock, where the solar wind slows down before giving way to interstellar space. Back then, the signal timing also shifted slightly. Not as much as now, but enough to be noticeable once you knew what to look for. It was like the spacecraft had a history of changing its voice whenever the space around it changed. Scientists at Stanford, familiar with Ronald Bracewell's old ideas about how probes might interact with cosmic environments, pointed out something interesting. Any object moving through a plasma-filled magnetic field will develop tiny electric currents along its surface. It's basic physics. You see similar effects when satellites pass through Earth's magnetosphere. Those currents can bleed into onboard electronics in subtle ways, altering how signals are generated without actually damaging the system. So one theory began to form. Voyager 2 isn't sending a new message. Its message is being reshaped by where it is. The spacecraft's antenna is like a voice box. The interstellar medium is like thick fog. As Voyager moves through regions with different plasma density and magnetic orientation, that fog bends the signal just enough to change the rhythm of what we hear on Earth. But there was a twist. The rhythm change wasn't random. It followed the structure of the magnetic field Voyager 2 was moving through, measured by its own magnetometer and confirmed by Voyager 1's earlier readings of the same region years before. In other words, the signal wasn't just distorted, it was being tuned by the environment itself. This is where the story stops being just about one old spacecraft. It becomes about what deep space does to information. Astronomers at the European Southern Observatory have long studied how light passing through interstellar dust changes color and polarization. The James Webb Space Telescope now does the same thing on a much grander scale, showing us how galaxies look different depending on what kind of cosmic fog sits between us and them. Voyager 2 is giving us the same lesson, but with radio waves instead of light. Out there, space is not just empty distance. It is an active medium that shapes every signal moving through it. That leads to an unsettling thought. If space can reshape Voyager's signal this easily, how many messages from the universe have we misunderstood over the years? Signals from pulsars, fast radio bursts captured by arrays built on Arecibo legacy designs, even the faint whispers James Webb picks up from the early universe. We assume what we receive is what was sent. Voyager 2 is quietly teaching us that's not true. And if that's the case, then some of the strange patterns we've labeled as noise in deep space data might not be noise at all. They might be the universe speaking through the medium itself. As Voyager 2 kept drifting farther from the sun, its signal grew weaker, not because the spacecraft was failing, but because the environment around it was getting thicker, heavier, with charged particles from the interstellar medium. Engineers at NASA's Jet Propulsion Laboratory had expected a smooth fade. What they saw instead were sudden drops and rebounds, like the signal was dipping in and out of fog banks. When the team lined these drops up with Voyager's plasma wave data, a pattern jumped out. The signal dips happened when Voyager crossed invisible boundaries in space, like underwater currents you can't see until you swim into them. These boundaries are known as interstellar plasma fronts. They form where the solar wind from our sun pushes against the wind of nearby stars. Voyager 1 first felt this wall years ago, when it crossed the heliopause. But Voyager 2's path is different. It's moving through a region that's more turbulent, where magnetic fields twist and reconnect. That means Voyager 2 isn't just passing through a wall, it's sliding along cracks in the wall. Scientists at Stanford, building on Ronald Bracewell's old ideas about interstellar probes and signal distortion, started to ask a wild question. What if the patterns we see in Voyager's signal aren't random damage, but the shape of the space itself? Imagine shining a flashlight through rippling water. The beam doesn't stay straight. It breaks into lines and waves. But those lines aren't created by the flashlight. They're created by the water. Voyager's signal may be doing the same thing as it passes through magnetic ripples in interstellar space. This led to a strange test. Researchers fed Voyager's distorted signals into models used by the Keck Observatory to correct for atmospheric blur when looking at distant galaxies. Those models are designed to undo distortion. When applied to Voyager's data, parts of the noise began to flatten into simple, repeating rhythms. Not words, not images, just structure. That alone doesn't mean anything is trying to talk to us. But it means the universe has structure deep enough to fake patterns. And humans are pattern hungry. Our brains are wired to see faces in clouds and meaning in static. The real danger isn't that Voyager heard something terrifying. It's that we might terrify ourselves by reading intention into a natural system we barely understand. Still, there was one detail that refused to fit neatly into the models. During one of Voyager 2's signal dips, the Deep Space Network logged a brief phase shift that didn't line up with plasma density, solar storms, or known magnetic filaments mapped by the European Southern Observatory. It was tiny. Most filters would have smoothed it out, but a few engineers flagged it because it happened twice, weeks apart, with nearly the same timing relative to Voyager's spin. That raised a quiet, uncomfortable question inside JPL. If space is doing the shaping, why did that one shift repeat? Not because it proves anything is out there, but because repetition is the one thing engineers are trained to notice. When chaos repeats, it stops looking like chaos. So now Voyager 2 is doing something no mission was designed to do. It's teaching us how to listen to space itself, and how easy it is to mistake the voice of the medium for the voice of something hiding inside it. As the data kept coming in, scientists at the Harvard Smithsonian Center for Astrophysics started comparing Voyager 2's signal distortions with something completely different. Background noise picked up by radio telescopes that were never meant to track spacecraft at all. Old Arecibo legacy recordings, taken years before the dish collapsed, contained faint hiss patterns from empty regions of sky. When those recordings were reanalyzed using the same filters applied to Voyager's signal, similar ripples appeared. Not the same pattern, but the same kind of distortion. That was the moment many researchers quietly changed how they framed the problem. This wasn't about Voyager sending a message back. It was about what space does to messages. The space between stars is not empty. It's threaded with magnetic fields, filled with charged dust, and shaped by shockwaves from ancient supernovae. The European Southern Observatory has mapped these magnetic filaments across vast stretches of the Milky Way. They form long, invisible strands, like spider silk stretched across the galaxy. When radio waves pass through those strands, they bend, split, and interfere with each other. Think of it like trying to listen to someone speak through a long tunnel with dripping water and echoing walls. The voice reaches you, but it's warped by the tunnel. Voyager's signal is traveling through a tunnel that is light years long. At the same time, the James Webb Space Telescope has been mapping cold clouds of gas and dust near the edge of the heliosphere. Some of these clouds are denser than expected. When Voyager's radio waves pass through them, the signal slows slightly, stretches in time, and then snaps back. That stretch and snap behavior can look like pulses when graphed. Here's the unsettling part. When the timing of those stretches was matched against maps from the Vera Rubin Observatory of faint stellar streams passing near our solar neighborhood, a loose alignment appeared. Voyager's strongest distortions happened when it crossed lines of sight that intersected those stellar streams. In other words, Voyager wasn't just crossing empty space. It was passing through crowded lanes of interstellar debris and magnetic flow left behind by stars that exploded millions of years ago. So the patterns we see may be the scars of ancient violence in our galaxy. That realization reframes everything. Voyager 2 isn't hearing whispers from something out there. It's hearing the echo of the Milky Way's long memory. Every supernova that ever went off near our region of space left ripples in the magnetic field. Those ripples still shape how signals travel today. Voyager's transmission is being bent by events that happened before Earth even formed. And yet, there's still that repeating phase shift. Researchers at NASA's Jet Propulsion Laboratory cross-checked it with Voyager 1's telemetry data. Voyager 1 passed through a different patch of interstellar space, but its signal showed a faint, similar blip years earlier. Not at the same location, not the same strength, but the same type of distortion, appearing when both spacecraft cross steep magnetic gradients. That points to something both simple and unsettling. There are edges in interstellar space that behave like lenses. When signals cross them, they pick up strange echoes. We're not decoding a message. We're mapping the shape of the ocean Voyager is swimming through. And for the first time, we're realizing that the ocean is rougher, deeper, and more structured than any. As Voyager 2 kept moving outward, engineers at NASA's Jet Propulsion Laboratory noticed something subtle but important. The signal distortions weren't random noise anymore. They clustered in bursts, like weather patterns in space. Weeks would pass with clean transmissions. Then suddenly, the signal would smear, stretch, and briefly lose clarity before snapping back into focus. That pattern lined up with what heliophysicists call interstellar weather. Just like Earth has storms and calm days, the space between stars has regions of turbulence and regions of calm flow. Data from the Hubble spectrograph helped here in an indirect way. Hubble has been studying how starlight changes as it passes through thin gas clouds near the boundary of our solar system. Those measurements show that some regions are calm, almost glassy, while others are chaotic, full of tiny magnetic whirlpools. When Voyager crossed one of those turbulent zones, its signal picked up extra distortion. When it drifted into calmer regions, the signal cleaned up again. This changed how scientists thought about the edge of our solar system. It isn't a neat border, it's a coastline. NASA, JPL teams began describing the heliopause, the boundary where the sun's influence ends, as a shifting shoreline. Sometimes it pushes outward, sometimes it pulls back. Voyager 2 is surfing that shoreline, moving in and out of rough interstellar currents. Every time it does, its signal carries the fingerprint of the region it just passed through. Then came another surprise. Radio astronomers using the Keck Observatory in Hawaii were studying distant quasars, incredibly bright objects powered by supermassive black holes. When they looked at how quasar radio signals flicker as they pass through interstellar space, they found flicker patterns that matched Voyager's distortions almost exactly. That means Voyager isn't unique. The same space weather that bends signals from distant galaxies is bending the tiny whisper from our spacecraft. This was a humbling moment. Voyager 2 isn't special to the galaxy. It's just another radio source being shaped by the same cosmic currents that shape everything else. But here's where it gets eerie. When scientists layered Voyager's path on top of maps of cosmic ray density made by detectors across Earth and by instruments on the International Space Station, they noticed small spikes in cosmic ray activity that lined up with Voyager's signal glitches. That suggests Voyager is passing through pockets of higher energy particles, like invisible radiation fog banks drifting through space. These fog banks are thought to be leftovers from ancient stellar explosions. Supernova shock waves compress magnetic fields and trap high-energy particles for millions of years. Voyager is moving through the ruins of long-dead stars. So when people say Voyager's signal sounds haunted, they're not entirely wrong in a poetic sense. It's whispering through graveyards of exploded suns. This also explains why decoding Voyager's transmissions feels harder now than it did decades ago. The deeper it goes, the more warped the radio path becomes. The universe isn't quiet out there. It's noisy in a way we're only just learning how to hear. And that brings us to the uncomfortable question scientists are now asking behind closed doors. If the space between stars is this turbulent, how reliable is anything we've ever heard from deep space? Fast radio bursts, mysterious repeating signals, strange blips from distant galaxies. How many of those are real sources? And how many are echoes of space itself twisting the message before it reaches us? Voyager 2 may be teaching us that the universe has been speaking in a distorted voice all along, and we've been blaming the speakers instead of the room. As Voyager 2 pushed deeper into interstellar space, scientists at the Harvard-Smithsonian Center for Astrophysics started comparing its data with measurements from another unlikely source, old Arecibo legacy data. Even though Arecibo is gone, decades of recordings of radio noise from deep space still exist. When those old patterns were lined up with Voyager's recent signal shifts, something clicked. The distortions Voyager is picking up match structures in the interstellar medium that were hinted at years ago but never confirmed. Thin sheets of charged gas, filament-like magnetic structures, vast bubbles carved out by ancient stellar winds. Back then, astronomers could only guess these structures were real. Voyager is now flying through them and feeling their effects directly. Think of interstellar space not as empty black nothingness, but like a giant three-dimensional ocean with invisible currents, eddies, and walls of moving plasma. Voyager is a tiny bottle drifting through that ocean, and every ripple it passes through leaves a mark on its signal. This also explains why Voyager 1 and Voyager 2, even though they are traveling in different directions, report similar patterns of turbulence at similar distances. The interstellar environment around our solar system appears to be part of a much larger bubble, shaped long ago by massive stars that exploded near the Sun's birth region. Data from the European Southern Observatory has shown remnants of these ancient supernova bubbles in nearby star-forming regions. And now Voyager is skimming the edge of one of those relic structures. Here's where the story takes a turn that even surprised the teams at NASA JPL. The plasma density Voyager 2 measured outside the heliosphere is higher than models predicted. That means the space around our solar system is thicker with charged particles than we thought. Not dangerous in a human sense, but important in a cosmic sense. It changes how cosmic rays enter our solar system. It changes how radiation moves, and it changes how signals from deep space reach Earth. This matters for everything we think we've detected from beyond our solar system. If the space around us acts like a lens, bending and shaping radio waves, then some mysterious signals from far-off galaxies might not be as exotic as they seem. They may be ordinary cosmic noise that got twisted into strange shapes on the way to us. This doesn't erase the mystery of fast radio bursts or odd repeating signals, but it forces astronomers to be more careful. Before calling something alien, they now have to ask, did the signal come in strange, or did space make it strange? And Voyager is now our only real weather balloon out there, drifting through this invisible storm system and sending back ground truth data. No telescope can replace that. Telescopes see from far away. Voyager is inside the storm. The deeper it goes, the more our old picture of the quiet, empty void falls apart. Interstellar space is alive with motion. Not life in the biological sense, but in the sense of constant movement, pressure, and change. It breathes, it flows, it carries scars from ancient explosions. And buried in Voyager's weak, fading signal is a map of that invisible world, written in tiny distortions that only careful listening can decode. The question now isn't just what Voyager will tell us next. It's whether we've been misunderstanding deep space for the last 50 years because we assumed it was quiet when it was never silent at all. Once scientists realized interstellar space isn't empty, but layered with moving plasma and magnetic walls, a new question followed naturally. What does that mean for the bubble our solar system lives inside? For decades, NASA Jet Propulsion Laboratory described the heliosphere like a smooth balloon inflated by the solar wind. The sun blows a steady stream of charged particles outward, and that creates a protective shell around the planets. Voyager 2 crossed that boundary and proved the shell exists, but it also proved it's not smooth. It's wrinkled, it's dented, it flexes and shifts like skin in a storm. Data from Voyager shows the heliopause, the edge of the sun's influence, moves in and out as pressure from interstellar space rises and falls. Sometimes the solar bubble shrinks, sometimes it swells. That means Earth's exposure to cosmic radiation isn't fixed. It slowly changes over decades and centuries, depending on what kind of interstellar environment we drift through. Researchers at Stanford, building on Ronald Bracewell's early radio astronomy, ideas about how signals move through space, started modeling how these shifting plasma layers act like filters. Certain frequencies pass through easily. Others get scattered or bent. Voyager's strange signal behavior now fits those models far better than any idea of malfunction ever did. And this brings up a deeper point that makes some scientists uncomfortable. For years, we treated the heliosphere as a shield that mostly keeps danger out. But Voyager's data suggests it's more like a living membrane. It doesn't just block, it exchanges. Interstellar particles leak in, solar particles leak out. The boundary is a mixing zone, not a wall. James Webb Space Telescope observations of nearby star systems show similar astrospheres around other stars. Some are huge, some are tiny. Some appear distorted by the interstellar environment they move through. This tells us our solar system is not special in having a protective bubble, but it might be special in how stable that bubble has been over the time life developed on Earth. If our heliosphere had been weaker during key periods of Earth's history, cosmic radiation levels on our planet could have been higher. Some researchers at the Harvard Smithsonian Center for Astrophysics have explored whether long-term changes in cosmic ray exposure might link to climate shifts or even mutation rates over millions of years. This doesn't mean space rays caused life or controlled evolution in a simple way, but Voyager is now giving real measurements of how much protection we actually have. Here's the quiet, unsettling part. Voyager's data suggests our solar system is moving toward a slightly denser region of interstellar space. Not a dramatic crash into a cloud, not a doomsday event, but a gradual change in the environment around us. Over tens of thousands of years, that could slowly compress the heliosphere, thinning our shield just a little. No alarms, no sudden danger. Just a reminder that the space around us is not fixed. The ocean our solar system swims in has currents, and we are drifting into different waters. And Voyager, a machine built in the 1970s, is the only thing out there quietly feeling those currents firsthand and telling us what the water feels like. The deeper it goes, the more it stops being just a spacecraft and starts feeling like a scout at the edge of a vast, moving wilderness that no human has ever touched. As Voyager 2 kept drifting outward, its instruments picked up low-frequency plasma waves that scientists at NASA, JPL, and the University of Iowa Plasma Wave Group had hoped to measure but never expected to hear so clearly. These waves weren't random noise. They rose and fell in patterns tied to shock waves from solar storms that happened years earlier near Earth. Think about that for a second. A flare erupts on the Sunday. Years later, Voyager hears the echo of that same event as a ripple in the thin plasma between stars. It's like shouting into a canyon so wide the echo comes back years later. Interstellar space, it turns out, remembers what happens inside our solar system. This memory effect changes how we think about space. The region beyond the heliosphere isn't a quiet graveyard of particles. It carries information. Disturbances travel through it. Waves spread through it. When massive solar storms hit the heliopause, they don't just bounce off. They push into interstellar space, sending ripples that Voyager can still detect long after Earth has forgotten the original event. Data cross-checked with Hubble spectrograph records and ground-based radio observations from the European Southern Observatory show similar plasma density changes around nearby stars. This means our sun is not unique in stirring the space around it. Stars leave fingerprints in the interstellar medium wherever they go. And here's where things get subtle but important. Voyager detected sudden jumps in plasma density just beyond the heliopause. These jumps look like invisible ridges, regions where interstellar particles pile up. Scientists think these form where our heliosphere plows into denser patches of the local interstellar cloud. Imagine a boat pushing through water. At the bow, water stacks up. Our solar system is doing the same thing in a very thin cosmic ocean. These ridges are not smooth. They come in layers. Voyager crossed at least 2 distinct plasma boundaries beyond the heliopause. That means interstellar space itself has structure. It's not one uniform soup. It's layered, clumpy, and shaped by ancient stellar winds, supernova shock fronts, and magnetic fields left behind by stars that exploded millions of years ago. Keck Observatory radio studies of gas clouds near the edge of our local interstellar neighborhood support this idea. They show that the space between stars is filled with overlapping shells of material from old stellar explosions. Voyager is drifting through the leftovers of events that happened long before Earth had trees or oceans. This adds a strange emotional weight to Voyager's journey. The signal coming back to Earth has passed through regions shaped by stars that died before humans existed. Every packet of data is traveling through ancient debris fields, magnetic scars from supernovae, and plasma stirred by stars that no longer shine. Voyager isn't just moving through space, it's moving through history, written in matter. And the deeper it goes, the clearer it becomes that the space between stars is not empty silence. It's a layered record of violence, creation, collapse, and motion. The quiet we see when we look up at the night sky is just the surface. Underneath it is a slow, restless sea of charged particles, waves, and memory. That's the environment Voyager 2 is now swimming through, alone, carrying a tiny, fading voice from Earth into a place that has been shaping stars and worlds long before we learned how to listen. When Voyager 2 crossed the heliopause, scientists at NASA's Jet Propulsion Laboratory didn't just celebrate, they went quiet. Not because the data was boring, but because the data didn't match the clean, simple models they had drawn on whiteboards for decades. The boundary between our solar system and interstellar space was supposed to be sharp, a kind of cosmic wall. Inside solar wind, outside interstellar medium, neat, clean, easy to label. That's not what Voyager found. Instead, the instruments showed a messy overlap zone, solar particles leaking out, interstellar particles leaking in, magnetic fields tangled together instead of snapping cleanly from one direction to another. The heliopause isn't a wall. It's more like a frayed shoreline where 2 oceans meet and mix. Voyager 1 and Voyager 2 crossed this boundary in different places and at different times. The fact that they measured different conditions tells us the edge of our solar system changes. It breathes. It swells and shrinks with the sun's activity. When the sun is active, the heliosphere pushes outward. When the sun calms down, interstellar space pushes back in. Harvard's Smithsonian Center for Astrophysics researchers use Voyager's data to update their models of heliosphere shape. And what they found surprised even them. The heliosphere isn't a smooth bubble. It's dented, stretched, and warped by the pressure of nearby interstellar clouds and by the motion of our solar system through the galaxy. Imagine driving through rain. The drops don't hit evenly on all sides of your windshield. They pile up more in front because you're moving forward. Our solar system is doing the same thing as it moves through the local interstellar cloud. Space is pressing harder on the front of the heliosphere than on the back. This means the edge of our solar system is lopsided. There are places where interstellar space pushes closer to the planets than we thought, and there are places where the sun's influence stretches farther than expected. Why does that matter? Because that boundary controls what kind of cosmic radiation reaches Earth. The heliosphere acts like a shield. When it weakens, more high-energy particles from distant supernovae and galactic sources can slip into the inner solar system. Researchers comparing Voyager data with long-term cosmic ray records from Arecibo legacy data and balloon experiments over Antarctica have seen clear links between heliosphere pressure and cosmic ray levels near Earth. In simple terms, the shape and strength of this invisible bubble affects the radiation environment of our planet. Over long time spans, that radiation can influence things like atmospheric chemistry and even mutation rates in living organisms. Voyager's quiet numbers are telling us that the solar system's protective bubble is not fixed. It changes, it bends, it leaks. And that means Earth doesn't live in a sealed bubble. We live in a moving window that opens and closes to the wider galaxy, depending on where we are drifting and how active our sun happens to be at that moment in cosmic time. As Voyager 2 moved deeper into interstellar space, its plasma instruments started returning readings that didn't line up with what models predicted for the local interstellar medium. According to textbooks, the space between stars is thin, calm, and fairly uniform. Not empty, but simple. Voyager says it's not simple at all. The density of particles outside the heliosphere was higher than expected. Not dangerously high, but high enough to force scientists at NASA's Jet Propulsion Laboratory and the European Southern Observatory to revise their models of how empty interstellar space really is. The space between stars isn't a vacuum. It's more like a fog, so thin you don't see it until you drive straight into it at insane speed. And Voyager is driving into it at over 35,000 miles per hour. What makes this strange is how structured that fog appears to be. The plasma waves Voyager picked up weren't random noise. They showed repeating patterns, ripples, and shifts that suggest turbulence in the interstellar medium. Not the kind of chaos you'd expect from nothingness, but the kind of motion you'd expect in a fluid. Astrophysicists at Stanford, building on Ronald Bracewell's early ideas about interstellar probes and signal environments, have long suspected that interstellar space might carry memory of past stellar explosions and magnetic storms. Voyager's data gives weight to that idea. The turbulence patterns match what you'd expect if shock waves from long-dead supernovae are still passing through the local interstellar cloud millions of years later. In other words, Voyager isn't just entering empty space, it's moving through the long, fading echoes of ancient stellar deaths. The James Webb Space Telescope and the Keck Observatory in Hawaii have both observed distant star-forming regions where shock waves compress gas and trigger new stars. Voyager is now swimming through the leftover ripples of similar events, only much closer to home and much older. This means the space around our solar system carries a record of what happened in our galactic neighborhood long before Earth even existed. And that raises an uncomfortable thought. If interstellar space is shaped by past explosions, then the environment our solar system moves through is not random, it's historical. We are drifting through the fossil remains of cosmic events. The galaxy is not a clean stage where stars are born and die in isolation. It's a messy place where old violence leaves fingerprints everywhere. Voyager's instruments are old by today's standards, but they're doing something no modern telescope can do, touching interstellar space directly. Hubble and James Webb can see light from far away. Voyager can feel the plasma, taste the particles, and measure the magnetic fields where no human-made object has ever gone before. That makes every small change in its data a message from a place we can't visit, can't sample, and can't return from. And as Voyager kept sending back numbers, another strange pattern started to show up in the data. The background noise of space wasn't quiet the way scientists expected. Beyond the heliosphere, Voyager's plasma wave instrument picked up a steady hum of low-frequency signals. At first, engineers at NASA's Jet Propulsion Laboratory thought it was just interference. Spacecraft get old, wires degrade, sensors drift. But the signal stayed clean, too clean. When teams compared notes with researchers at the European Southern Observatory and radio astronomers who had worked with Arecibo legacy data, the pattern looked familiar. This wasn't random static. It matched the natural plasma oscillations of the interstellar medium, the thin gas between stars. In simple terms, Voyager was hearing the galaxy itself. Imagine stepping out of a quiet room into a busy street. You don't hear one voice. You hear a whole crowd blended into a low roar. That's what Voyager picked up. The sound of charged particles moving through magnetic fields, stretching across light years. It's the closest thing we have to listening to the Milky Way breathe. What shocked scientists wasn't just that the sound existed, it was how stable it was. Space is violent. Supernova shock waves ripple through the galaxy. Stars flare. Magnetic storms erupt. You'd expect chaos in these signals. But Voyager's data showed long periods of calm, steady oscillation, like a deep, slow heartbeat. Researchers at Stanford, building on early ideas from Ronald Bracewell about interstellar communication and cosmic signals, pointed out something unsettling. Stable patterns across huge distances mean the interstellar medium is more organized than we once believed. This challenges the old picture of deep space as empty and random. It isn't empty. It isn't random. It's structured, shaped by magnetic fields and flows of plasma that connect star systems like invisible currents in an ocean. And those currents touch us. When the heliosphere presses against this interstellar ocean, waves form along the boundary. Voyager's readings suggest these waves can grow and collapse, changing how particles slip into our solar system. That means the amount of cosmic radiation that reaches Earth may rise and fall over long periods, not just because of the sun, but because of the galactic environment we're sailing through. So here's the quiet, unsettling truth. Our planet doesn't just live under the sun's influence. It lives inside a moving pocket of space that drifts through a living galaxy. Voyager 2 is showing us that the space beyond our solar system isn't dead silence. It's a vast, humming field of energy, and we are passing through it right now. As Voyager kept drifting farther out, another layer of the mystery started to form around something even more basic: direction. For decades, scientists assumed that once a probe crossed into interstellar space, conditions would change in messy, uneven ways. Different densities here, random magnetic fields there. But when Voyager 1 and Voyager 2 compared notes from two totally different exit points of the heliosphere, the results were oddly similar. Teams at NASA's Jet Propulsion Laboratory noticed that the direction of the magnetic field just outside our solar system lines up almost perfectly with the magnetic field inside it. That shouldn't happen by accident. If the sun's bubble were just plowing through random space, the fields should clash and twist. Instead, they seem to shake hands. The interstellar magnetic field gently drapes around the heliosphere, forming a smooth boundary. Researchers working with data from Hubble spectrograph records and modeling groups at the Harvard Smithsonian Center for Astrophysics showed that this alignment reduces turbulence at the edge of our solar system. In plain words, our solar system is not crashing through space. It's gliding. This changes how we think about cosmic shielding. The heliosphere acts like a protective cocoon, deflecting a huge amount of high-energy cosmic rays that would otherwise slam into Earth's atmosphere. The smoother the boundary, the more stable that shield becomes. But here's the catch. Stability also means vulnerability to long-term shifts. If the galactic magnetic field changes over tens of thousands of years, our shield changes with it. That has real consequences for life on Earth. There's growing evidence discussed in long-term climate studies and cosmic ray research at institutions like Caltech and the Max Planck Institute that shifts in cosmic radiation can influence cloud formation and even mutation rates in living organisms. We're not talking sci-fi mind control. We're talking about tiny nudges that, over millions of years, can shape evolution. Now add one more strange detail Voyager uncovered. Beyond the heliopause, the density of charged particles increases sharply. Space isn't thinning out the way you'd expect as you leave the sun's influence. It's getting thicker, like stepping out of a quiet bay into a deeper current of water. The galaxy isn't a vacuum. It's a medium, a slow-moving, charged sea that presses back against our solar bubble. When scientists at the European Southern Observatory compared this with observations of other star systems, they realized our sun might be traveling through a region of space that's denser than average. That means our cosmic neighborhood right now is not normal. It's a patch of the galaxy with stronger fields, more particles, and more energy flowing through it. So when Voyager sends back those calm, steady signals, it's not telling us space is peaceful. It's telling us we're in a wide river of invisible forces. And our entire solar system is floating through it together, like a small boat in a current we barely understand. And that river of invisible forces doesn't just push on our solar system from the outside, it leaks in. When Voyager crossed the boundary, its particle detectors recorded something subtle but important. Low-energy cosmic rays that were once blocked by the heliosphere began to appear inside the bubble in higher numbers. At the same time, some of the high-energy particles coming from deep space dropped off. It's like opening a door between two rooms with different temperatures. The air doesn't rush in all at once. It slowly mixes. Scientists at NASA's Jet Propulsion Laboratory and teams working with the Voyager plasma wave subsystem describe this as a slow breathing of the heliosphere. The boundary isn't a wall. It's more like a membrane. It flexes, stretches, and lets certain things through while keeping others out. The shape of that membrane changes as the sun's activity rises and falls in its one-year cycle. Here's where it gets quietly unsettling. When the sun is calm, the heliosphere shrinks. When the sun is active, it puffs out. Voyager's long timeline of data shows that during solar minimums, more interstellar particles slip closer to Earth. That means the space environment around our planet isn't fixed. It's alive, in slow motion, changing with the sun's mood. Researchers at Stanford, building on Ronald Bracewell's early work on interstellar probes and cosmic environments, pointed out that any technology or life traveling between stars would have to deal with these shifting membranes of stellar bubbles. In other words, interstellar space is not just empty distance, it's layered territory. Now zoom out even further. Observations from the Hubble Space Telescope and radio surveys that include legacy Arecibo data show that our galaxy is threaded with vast magnetic structures, like invisible highways. These filaments guide charged particles across thousands of light years. Our solar system is moving through one of these streams right now. That means what Voyager is tasting out there is not random soup. It's part of a much larger flow of energy across the Milky Way. This raises a quiet but heavy question. If our solar system is passing through regions with different particle densities and magnetic fields, then Earth's long-term radiation environment changes over cosmic time. The background level of cosmic rays that reaches our atmosphere today is not what it was a million years ago, and it won't be the same a million years from now. Over deep time, those changes can shape biology, climate patterns, and even the stability of satellites and technology we rely on. Voyager isn't sending us a horror story. It's sending us a reminder. We live inside a moving bubble, drifting through a charged ocean. The conditions that protect us are real, but they're temporary. The shield around our world is strong, but it's not permanent. Cosmic rays don't just pass by Earth like distant fireworks. Some of them slam into our upper atmosphere and shatter atoms apart. When that happens, they create showers of secondary particles that rain down toward the surface. Most of this gets absorbed high above us, but a small fraction makes it all the way down. Physicists at the Harvard Smithsonian Center for Astrophysics have studied how these particle showers can slightly increase cloud formation by ionizing air molecules. It's not dramatic on any given day, but over long spans of time, changes in cosmic ray levels can nudge climate patterns in subtle ways. So when Voyager measures a shift in the particle mix outside the heliosphere, it's not just space trivia. It's a signal that the background radiation reaching Earth can change as our solar system moves through different regions of the galaxy. The Milky Way is not uniform. It has dense clouds, quiet voids, and magnetized filaments. Our planet is riding through all of it on a slow, billion-year road trip. And there's another layer to this that almost nobody thinks about. Those same cosmic particles interfere with electronics. Engineers at NASA, JPL, and ESA have to harden spacecraft computers because a single high-energy particle can flip a bit in memory, causing glitches. On Earth, airlines adjust flight paths over polar regions during solar storms because radiation levels spike at high altitudes. The deep space environment Voyager is sampling is the raw version of the space weather that can one day affect our grids, satellites, and navigation systems here at home. Now think about what that means for something traveling between stars. Any probe, natural object, or unknown technology drifting through interstellar space is bathing in this radiation nonstop. Over decades, centuries, or millions of years, that radiation erodes materials, changes chemistry, and slowly rewrites structures at the atomic level. This is one reason researchers at the European Southern Observatory and teams using the Keck Observatory in Hawaii take such interest in how interstellar dust grains change over time. These grains are like tiny travelers. They pick up scars from the environments they pass through. Voyager's message, in a way, is about endurance. It's telling us what survives in the space between stars. It's showing us the raw conditions any traveler would face. The cold is extreme. The radiation is constant. The magnetic fields are strong enough to shape paths across light years. Nothing moves through this space unchanged. And that circles back to something unsettling. If anything artificial had been drifting through interstellar space for a very long time, Voyager's data hints that it wouldn't look fresh. It would carry the fingerprints of the galaxy itself. Radiation damage, altered surfaces, changes in structure at microscopic levels. The galaxy leaves marks on everything that passes through it. We tend to imagine space as clean and empty. Voyager is showing us that deep space is more like weathered wilderness. It shapes whatever enters it. Now, zoom your mind out even farther, because Voyager's data doesn't just tell us what space is like today. It hints at how space changes over time and how our solar system moves through different neighborhoods of the Milky Way like a ship crossing invisible seas. Astronomers at the European Southern Observatory and researchers using the Vera Rubin Observatory have mapped giant clouds of gas and dust drifting between stars. Some regions are thick with particles. Others are almost empty. The Sun, carrying Earth and every planet with it, is slowly moving through these regions as the galaxy rotates. Right now, we're passing through what's called the local interstellar cloud, a thin veil of gas that surrounds our solar system. Voyager 1 is measuring its density, temperature, and magnetic structure directly, something no telescope on Earth could ever do. And here's the strange part. The local interstellar cloud isn't stable. It has edges, ripples, and gradients, like fog drifting across a highway. As the Sun moves, the amount of interstellar material flowing into the heliosphere changes. That changes how much cosmic radiation reaches the inner planets. It changes how our magnetic bubble flexes and shrinks. Over long stretches of time, this could even influence how much radiation reaches Earth's atmosphere. Researchers at NASA JPL have modeled how past passages through denser interstellar regions may have compressed the heliosphere in ancient eras. When that happens, more cosmic radiation can leak in. Some scientists have even looked at links between these galactic passages and periods of higher mutation rates in life on Earth, though this is still debated and far from settled science. The point is not that space directly controls life, but that our planet is not sealed off from the galaxy. The galaxy reaches into our environment in quiet, slow ways. This makes Voyager's role feel bigger than just a lonely probe drifting into darkness. It's like a scout sent ahead of our entire civilization. It's measuring the terrain before we ever think about traveling between stars. Every number it sends back is a warning label on deep space. This is the temperature you'll face. This is the radiation you'll endure. This is how magnetic fields will push and pull you when you're far from any star's protection. And there's a poetic twist to this. Voyager is doing all of this with technology from the 1970s. Its radio signal is faint. Its power comes from decaying plutonium. Yet, its data is still reshaping how modern scientists think about the boundary between our solar system and the wider galaxy. Teams at the Harvard Smithsonian Center for Astrophysics and scientists working with Hubble spectrograph records use Voyager's readings as ground truth. Telescopes can infer what interstellar space might be like, but Voyager is actually there, touching it. This is why scientists get uneasy when people talk about deep space travel like it's just a longer road trip. The space between stars is not empty. It is active, harsh, and slowly destructive. It grinds down anything that moves through it. Voyager is showing us the price of wandering beyond our solar home. And there's another layer to this story that almost never makes the headlines. Voyager isn't just flying through gas and magnetic fields. It's moving through a region shaped by ancient explosions. Long before humans existed, before Earth had complex life, nearby stars lived fast and died young. When massive stars explode as supernovae, they don't just light up the sky. They flood nearby space with shock waves, radiation, and heavy elements. Over millions of years, these explosions carved out what scientists call the local bubble, a vast, low-density cavity in the Milky Way that our solar system now sits inside. Astrophysicists at institutions like the Harvard Smithsonian Center for Astrophysics and researchers using data from the European Southern Observatory have traced the shape of this local bubble by mapping hydrogen gas and X-ray emissions. The bubble is thought to be the result of multiple supernova blasts over the last 10 to 20 million years. Voyager 1 is now skimming the inner edge of this ancient scar in the galaxy, where shock-heated gas meets cooler interstellar clouds. Why does this matter? Because supernovae don't just sculpt space, they seed it. The iron in your blood, the calcium in your bones, the oxygen you breathe were forged in stars that exploded long before the sun was born. Voyager is passing through the leftovers of stellar deaths that helped make life on Earth possible. The particles hitting its instruments are, in a very real sense, pieces of ancient stars brushing against a machine built by humans. There's also a quiet danger here. Supernova remnants carry high-energy cosmic rays. These are particles moving so fast that they can damage DNA, disrupt electronics, and slowly erode spacecraft materials. Scientists at NASA, JPL, and teams studying Voyager's plasma wave data have seen how the density of energetic particles changes as the probe moves through different patches of interstellar space. This is a preview of the radiation environment any future interstellar craft would face for decades or centuries. So when people dream about starships, sleeping pods, and humans crossing to other suns, Voyager is the cold reality check. Deep space is not just far away, it is chemically violent and physically unforgiving. Even the quiet parts are loud in radiation. Yet, there's something oddly hopeful in this. Voyager is still talking to us. Its whisper of radio waves crosses billions of kilometers and reaches antennas on Earth. The Deep Space Network, run by NASA JPL, still listens for that tiny signal. It's proof that even across the emptiest reaches we know, connection is possible. Weak, delayed, fragile, but real. And that idea changes how we see our place in the galaxy. We're not just sitting on a rock around a star. We're part of a moving system, drifting through a living, changing cosmic environment shaped by explosions, magnetic storms, and ancient stellar debris. Voyager is our first sense organ in that wider body. Now, here's the part that almost no one talks about because it doesn't sound dramatic enough for headlines, but it might be the most important clue of all. Voyager's instruments aren't just picking up particles and fields, they're picking up change. Slow, steady, subtle change. The kind of change you only notice when you compare data across years. Scientists at NASA's Jet Propulsion Laboratory have been watching how the pressure around Voyager shifts over time. Not pressure like air pressure, but the pressure created by charged particles, radiation, and magnetic fields pushing against each other. What they're seeing is that interstellar space is not uniform. It's patchy, lumpy, uneven, like weather, but on a scale so large it makes our planet's storms look like dust motes. Some regions are dense with charged particles. Others are almost empty. Some are calm. Others are turbulent, filled with magnetic ripples and waves. When Voyager drifts from one region into another, its instruments record sudden changes in particle speed and density. To scientists at places like the Harvard Smithsonian Center for Astrophysics, this is like finally feeling the texture of a place we've only seen from afar. Before Voyager crossed the heliopause, most models of interstellar space were based on distant observations and theory. Telescopes like Hubble and radio surveys, including old Arecibo legacy data, gave us big picture maps. But those maps are blurry. Voyager is giving us the first close-up, and the close-up says the space between stars is messy. This matters because our entire solar system is moving through this mess. The sun isn't parked in one calm region of the galaxy. It's plowing through clouds of gas and dust. Over millions of years, the solar system moves from one interstellar neighborhood to another. Each neighborhood has different radiation levels, different particle densities, different magnetic conditions, and those differences can slowly change how much cosmic radiation reaches Earth. Some astrophysicists think past shifts in our interstellar environment may have nudged Earth's climate or influenced how much radiation reached the surface. There's ongoing work at universities like Stanford and research groups using data from space probes and cosmic ray detectors to understand how changes in interstellar space might connect to long-term changes on planets like ours. So Voyager isn't just telling us what space is like out there. It's giving us hints about what our cosmic weather forecast might look like millions of years from now. And there's something quietly humbling about this. We like to think of the solar system as a stable home, but in reality, it's a moving ship. The sun carries Earth, Mars, Jupiter, and all the rest through a galaxy full of invisible currents. We don't steer, we drift. Voyager is simply the first scout to swim ahead of the ship and report back what the water feels like. And the water isn't empty. As Voyager keeps drifting farther from the sun, the data gets thinner, weaker, and harder to read. Its power source, the radioisotope generator, is slowly fading. Engineers at NASA's Jet Propulsion Laboratory have already shut down non-essential instruments to keep the core systems alive. Every year, the signal gets a little quieter. One day, the spacecraft will go silent for good. No goodbye message, just a final whisper, then nothing. That's what makes these last readings feel heavy. We're in the final chapter of the longest space journey ever made by anything built on Earth. And here's the strange part. The deeper Voyager goes, the more it's teaching us how small we are, not just in distance, but in time. The light from nearby stars takes years to reach us. The radio messages Voyager sends back take more than 22 hours to arrive. That means every time engineers at JPL adjust Voyager systems, they're talking to the past. They send a command. They wait almost a full day to see if it worked. When the signal comes back, it's already old news. The spacecraft is always ahead of us in time, living in a future we can't quite reach. Astronomers at places like the European Southern Observatory and researchers working with data from the James Webb Space Telescope spend their lives reading old light. Webb looks at galaxies as they were billions of years ago. Hubble's spectrograph records show us stars in earlier stages of their lives. Voyager is the same idea, but personal. It's a machine we built that is now living in a place we can't visit and a moment we can't catch up to. And there's another layer to this that feels almost emotional. Voyager 1 and Voyager 2 carry the golden record, a time capsule of Earth, sounds of waves, heartbeats, music from different cultures, greetings in many languages. A small metal message drifting between stars. It's easy to laugh at the idea that aliens will ever find it. The odds are tiny, but that's not really the point. The golden record wasn't made for aliens. It was made for us. It's proof that at some point in our history, we looked up at the dark and decided to send a piece of ourselves into it. Not a weapon, not a warning, a hello. Carl Sagan and the team who worked on it knew Voyager would likely never be found. They did it anyway. Because sending that message changes how you see yourself. You stop seeing Earth as just a place. You start seeing it as a tiny island of life in a vast ocean of cold. Voyager is now far beyond the reach of any rescue, repair, or upgrade. No rocket we have can catch it. No mission we can design today can meet it out there. It's alone in interstellar space, carrying our data back to us, bit by bit, until it can't anymore. And when it finally goes silent, it won't crash, it won't explode, it will just keep drifting. Quiet, dark, a small human-made object moving between stars, long after every person alive today is gone. And that might be the most unsettling part of the story, because Voyager isn't just exploring space. It's showing us what it means to leave a trace in a universe that doesn't notice when we pass through it. Out there, beyond the heliosphere, where the sun's influence finally thins out, space isn't empty. It's filled with thin gas, stray atoms, dust, and invisible fields of energy moving between stars. This region is called interstellar space, and Voyager 1 crossed into it back in 2012, confirmed by plasma wave measurements analyzed by scientists at NASA's Jet Propulsion Laboratory and the Harvard Smithsonian Center for Astrophysics. Voyager 2 followed in 2018, giving us the first two direct probes of a place no spacecraft had ever touched before. And what they found wasn't silence. The instruments recorded a constant hum of plasma waves. the sound of charged particles vibrating in the thin gas between stars. It's faint, but it's there, like a low wind moving through a forest you can't see. This alone shocked researchers, because models based on data from the Arecibo Legacy surveys and ground-based observatories had suggested interstellar space near our solar system might be far calmer. It isn't. It's alive with motion, pressure, and energy. Voyager also showed us that the boundary of our solar system is messy. The heliopause, the edge where the solar wind meets interstellar material, isn't a clean shell. It's more like a wrinkled, shifting membrane. The magnetic field lines twist, reconnect, and ripple. This was confirmed by magnetometer data that teams at JPL and the European Southern Observatory later compared with computer models of stellar wind interactions around other stars. This matters because that boundary is our shield. The heliosphere deflects a huge amount of cosmic radiation that would otherwise flood the inner solar system. Voyager's data revealed that once you cross that boundary, radiation levels jump fast. The space between stars is harsher than anything astronauts have ever faced. This is one of the biggest reasons interstellar travel isn't just hard, but dangerous in ways we're only starting to understand. And then there's the particles Voyager detected that shouldn't really be there. Some of the high-energy cosmic rays Voyager recorded have energies that don't match simple models of supernova shockwaves. Astrophysicists working with data from the Keck Observatory in Hawaii and the Stanford radio astronomy groups studying Ronald Bracewell's early concepts of interstellar probes have suggested that these particles may come from complex magnetic traps formed by colliding stellar winds. In simple terms, space between stars isn't just a highway. It's full of whirlpools and crosswinds that bend and twist radiation in strange ways. This changes how we think about what's out there between solar systems. It's not a calm, empty void. It's an active environment with structure, weather, and hazards. The kind of place that slowly erodes anything that travels through it. And that brings us back to the signal that set off the alarms. When engineers at NASA's Deep Space Network started noticing subtle changes in Voyager 2's transmission patterns, it wasn't because Voyager sent a message in words. It was because the noise around the signal changed. The background hiss wasn't stable. It pulsed, not in a clean rhythm, but in clusters that didn't match known solar storms or known sources of cosmic radiation. Teams compared the timing with data from solar observatories and space weather models. Nothing lined up. At first, this was blamed on aging hardware. Voyager is old. Its transmitter was built in the 1970s. But when the same pattern showed up in data from multiple Deep Space Network antennas at different times, the explanation got weaker. The environment around Voyager was doing something unusual. And that environment was shaping the signal we were receiving. In other words, whatever Voyager was passing through was changing the way its radio waves traveled back to Earth. For weeks, teams at NASA's Jet Propulsion Laboratory kept digging into those strange distortions in Voyager 2's signal. They cross-checked them against space weather models from the National Solar Observatory, compared them with plasma data from Voyager 1, and even pulled old records from the Arecibo Legacy archive to see if anything like this had ever shown up before. Nothing matched. The distortions weren't coming from the Sunday. They weren't coming from Earth. They weren't even coming from known interstellar plasma behavior mapped by the European Southern Observatory's models of stellar wind interactions. The only place left was the space Voyager was flying through right now. Then something unsettling happened. The signal changes lined up with sudden shifts in the local magnetic field measured by Voyager's own magnetometer. Every time the background plasma density spiked, the radio noise warped in the same narrow band of frequencies. This wasn't random interference. It was the environment itself acting like a lens, bending and shaping the signal in real time. Scientists working with the Harvard Smithsonian Center for Astrophysics described it as Voyager flying through ripples in the fabric of interstellar plasma, like a boat cutting across invisible waves at night. The climax came when modelers at JPL ran new simulations using data from the James Webb Space Telescope on how charged dust and ionized gas clump in the regions between stars. The model showed that under rare conditions, interstellar plasma can form temporary, filament-like structures that trap energy and vibrate. When a radio signal passes through one of these filaments, it doesn't just weaken. It gets shaped, delayed, and subtly modulated. What we were hearing wasn't a message. It was Voyager's voice being warped by a living, shifting medium between stars. The fear wasn't that something had spoken to us. The fear was realizing how little we understand about the space our probes are already traveling through. So here's the truth behind the headlines. Voyager 2 didn't receive a terrifying message from deep space, but it did reveal something just as unsettling. The space between stars isn't empty, quiet, or predictable. It has structure. It has weather. It can twist signals, trap energy, and change in ways our old models never predicted. Thanks to Voyager 1 telemetry, Hubble spectrograph records, and new insights from Webb and teams at NASA JPL, we now know that interstellar space is an active environment, not a blank void. The real shock isn't that something is talking to us. It's that the road between stars is far more alive than we ever imagined, and we're only just learning how dangerous and strange that road can be. If you want to follow what Voyager discovers next, as it keeps drifting deeper into this unknown space, watch the next video on your screen and stay with the story as it unfolds.